So when those smaller beta particles that are more dispersed precipitate out, we can have a large number of them precipitating or a smaller number. They can be smaller in size or larger in size. As well, they can exhibit something called coherence. So if we have coherent precipitates, it means that the matrix, so the alpha matrix and the beta precipitates are fairly continuous in terms of the crystal structure and the boundaries, whereas with less coherence we would have more distinct boundaries between them. All of these and there's other factors as well, can impact the resulting properties of our precipitate hardened material. But what you really want to imagine is that when we're moving from C to D, we have our supersaturated solid solution, and then we have these little tiny particles precipitating out and kind of forcing their way into the structure. But our sample geometry is the same. Our sample isn't changing. So you can imagine that these little particles are kind of, for lack of a better description, forcing themselves into the matrix and thereby causing these very, very slight micro deformations. So we're straining our matrix. And these strains, or lattice strains, are caused by the microscopically small precipitate particles and will actually inhibit or restrict dislocations. So this is the mechanism by which precipitate hardening alters mechanical properties. However, if we go back and we look at the difference from from A to B, so from our original sample to our annealed sample, there's a pretty distinct difference in the structure, where we have alpha and beta initially, and then we have beta dissolved at point B. And so this can also impact material properties. And we're seeing annealing cause atoms to migrate in the crystal lattice, and what this actually does is decrease the number of dislocations and leads to a change in material properties as well. So what are the actual changes in material properties that we should see? What we say is that, I'll write it out here, dislocations are often the dominant carriers of plasticity. So from C to D, we are restricting / inhibiting our dislocations. Whereas from A to B, as we have atoms migrating in the crystal lattice, we're actually decreasing the number of dislocations, and in that way the alteration allows dislocations to propagate more easily. So we're actually enabling dislocations. Motion. And we have this concept here, our little cloud, of dislocations being related to plasticity. So to draw this out, if we consider a stress strain curve, something like we saw in Lab 1, and we have a given material. I need some more colors here. Let's do a red. We have a material with a stress strain curve. We have our yield point around here. If we restrict or inhibit dislocations, we're actually delaying the onset of plastic deformation. So we are shimmying our yield strength up here and increasing the size of the elastic regime and delaying the onset of plastic deformation. In contrast, the changes that occur from annealing actually allow plastic deformation to occur earlier on, and sometimes we might see a change in the modulus as well, so something like that. This is, okay, so this is C to D here, and this is A to B here. So this is how these changes at the structural level are going to manifest on a given stress strain curve. So we can see that we're having definitely some impacts on yield strength, definitely some impacts on ultimate strength, and there's potentially, with regards to annealing, there may be some changes in the modulus as well, depending on the process itself. So now we've kind of seen the precipitate hardening process, what it looks like, again, on our phase diagram, what the process looks like over time. We've seen the changes in microstructure occurring, and now we're starting to understand how this manifests in the stress strain curve. So all of this is going to be the theory that your lab 4 is based on.